In the middle of the vast Pacific, on the youngest and most fragile volcanic island chain on Earth, the state of Hawaii is doing something that, on paper, looks like engineering suicide. They are deliberately pumping hundreds of thousands of gallons of freezing, high-pressure seawater every minute, from nearly a kilometer beneath the ocean surface, straight onto one of the hottest, most barren lava fields on the planet. This is Kona, Big Island, a landscape of black basalt that absorbs solar heat like a furnace, where surface temperatures regularly exceed 50 degrees Celsius. Rainfall is minimal and the ground has almost zero topsoil. The entire region sits on active volcanic terrain, prone to earthquakes, lava flows, and the constant threat of catastrophic eruptions. History gives us a stark warning. In the 1930s, the Soviet Union attempted a similar great transformation of nature by diverting massive Siberian rivers southward, only to trigger ecological disasters, salinization, and the near death of the Aral Sea, one of the worst man-made environmental catastrophes ever recorded. By every conventional logic, pulling cold, nutrient-rich deep seawater onto this unstable, scorching lava plain should have been a recipe for disaster. Massive corrosion, seismic damage to pipelines, ecological disruption, and financial ruin. Yet satellite imagery tells a different story. Where there was once endless black rock, vivid green raceways and aquaculture tanks now sprawl across hundreds of acres. The facility is thriving, producing millions of pounds of premium seafood and superfoods, and generating a $150 million annual economic impact. So here lies the central paradox. How can the exact same deep ocean water, when brought to the surface of a dead volcanic desert, produce both the potential for catastrophe and one of the most successful examples of sustainable high-value farming on Earth? First, let's carefully examine the key reasons that led to the construction of this seemingly impossible project. Back in the early 1970s, the Big Island's Kona coast was a stark reminder of nature's raw power. This volcanic wasteland, forged from eruptions like those of Mauna Loa and Kilauea, spans over 2,000 square miles of black basalt rock, absorbing heat like a giant solar oven, with surface temperatures hitting 50 degrees Celsius or more. Rainfall here averages just 10 to 20 inches a year, far less than the 60-plus inches needed for traditional farming. Freshwater was, and still is, precious and scarce, forcing Hawaii to import a staggering 85 to 90% of its food supply, costing the state billions annually and leaving it vulnerable to global disruptions like supply chain breakdowns or climate events. Enter the visionaries at the state of Hawaii. In 1974, they founded the Natural Energy Laboratory of Hawaii Authority, NELHA, with a bold gamble. Tap into the ocean's hidden depths to unlock resources that could revolutionize energy and agriculture. The key insight: deep seawater at 600 to 1,000 meters below the surface isn't just cold. It's a nutrient powerhouse, packed with nitrates, phosphates, and minerals at concentrations 10 to 20 times higher than surface water, and virtually sterile, free from the bacteria and pollutants that plague coastal zones. This wasn't just about survival. It was about turning a liability, the island's isolation and barren land, into a strength. By harnessing deep seawater, NELHA aimed to mimic cold water ecosystems in the tropics, potentially slashing food import dependency and creating jobs in a state where agriculture had shrunk to less than 1% of GDP. But turning this dream into reality required engineering on an epic scale. Construction kicked off in the early 1980s at Keyhole Point, a rugged coastal site with a steep underwater drop-off, ideal for reaching depths quickly without miles of horizontal piping. Teams deployed specialized marine vessels to drill into the seabed, laying the first 18-inch diameter pipeline in 1981. Over the next decades, they scaled up massively. By the 1990s, the Maine deep seawater line ballooned to 55 inches, 1.4 meters, wide, one of the largest seawater intakes ever built, capable of pumping up to 100,000 gallons per minute against immense pressure and gravity. These composite pipes, engineered to resist corrosion and withstand depths equivalent to the height of 3 Eiffel Towers stacked, were anchored with precision amid seismic risks from active volcanoes. Onshore, powerful pumping stations, each housing massive electric motors, lift the water uphill by 100 to 200 meters to the 870-acre host park. A web of underground distribution lines, spanning several kilometers, delivers the flow to tenant facilities. The total cost? Hundreds of millions of dollars, funded by state and federal grants, with ongoing maintenance running into the millions annually. By 2025, upgrades include AI-monitored sensors and redundant systems to handle everything from hurricanes to lava flows. Now that we've seen the colossal effort it took to bring this deep ocean water to the surface, let's get to the heart of the magic. How does this cold, ancient seawater actually make lobsters, abalone, and supernutrient algae thrive on a lava field that would otherwise be lifeless? The secret is simple yet brilliant: a continuous flow-through system powered by the deep seawater. Unlike traditional aquaculture farms that recirculate the same water over and over, which can build up waste and disease, NELHA set up pumps fresh, pristine deep seawater from 600 to 1,000 meters deep and lets it flow straight through the tanks, raceways, and ponds before returning it to the ocean. This constant renewal mimics the natural upwelling of nutrient-rich cold water in the open sea. Except here, it's engineered and delivered on land. Why is this so powerful? First, the temperature. At just 5 to 7 degrees Celsius, around 43 degrees Fahrenheit, the deep seawater creates the perfect cold environment for species like Maine lobster and abalone that normally live in chilly northern or deep waters. In Hawaii's tropical heat, no amount of air conditioning could replicate this naturally. Deep seawater does it for free, using the ocean's own thermal stability. Second, purity. Drawn from depths where sunlight never reaches, this water is almost completely free of surface bacteria, pathogens, parasites, and pollutants. It's one of the cleanest natural waters on the planet, drastically reducing disease outbreaks and the need for antibiotics or chemicals. Third, nutrients. Deep water is loaded with dissolved nitrates, phosphates, silicates, and trace minerals, up to 10 to 20 times more than surface seawater, acting like a natural fertilizer that supercharges growth. For Maine lobster, Homerus americanus, the classic cold water icon, NELHA once ran full aquaculture trials and still supports holding/revival operations. The process starts with live lobsters airshipped from the U.S. mainland, packed in gel refrigerant for the long flight. Upon arrival, they are immediately placed in tanks filled with chilled, pathogen-free deep seawater at 43 degrees Fahrenheit. The constant flow oxygenates the water perfectly and flushes away waste, allowing stressed lobsters to recover quickly and stay healthy for weeks or months. In full grow-out experiments, like those by Kona cold lobsters in the 1980s, 1990s, juvenile lobsters grew faster thanks to high oxygen levels and zero contamination, molting more efficiently and reaching market size in shorter cycles than in the wild. The cold, deep seawater reduces metabolic stress, improves shell quality, and keeps the meat firm and flavorful. While full-scale farming has shifted more toward premium holding and distribution today, the mechanism proves the concept. Cold, clean, flowing deep seawater turns a tropical island into lobster paradise. Next door, Big Island Abalone operates the largest abalone farm in the U.S., with millions of Japanese northern abalone, Abalone, growing across 10 acres of tanks. The process begins in a controlled hatchery. Broodstock spawn eggs that hatch into tiny villager larvae. These delicate babies are nurtured in nursery tanks with a blend of deep seawater and warmer surface water to kickstart development. As they settle and grow shells, they move to grow-out tanks where pure cold deep seawater flows constantly, providing the ideal 12 to 15 degrees Celsius environment, abundant minerals for shell formation, and ultra-clean conditions that boost survival rates to 80 to 95%. The abalone graze on specially grown dulse algae, a red seaweed, cultivated right on-site using the same nutrient-rich deep seawater. Growth is steady and impressive. From tiny juveniles at 1 month old, they reach market size around 8 to 10 centimeters in 3 to 5 years, developing the prized red hue, firm texture, and rich flavor that fetch premium prices in Japan and the US. The constant flow prevents fouling, minimizes disease, and delivers the minerals needed for rapid shell and meat development, turning a slow-growing delicacy into a sustainable, high-value crop. Finally, Cyanotech Corporation, the world's leading spirulina producer, turns deep seawater into a superfood powerhouse. Their massive raceway ponds, covering 90 acres, are filled with a mix of fresh aquifer water and supplemental deep seawater for minerals like magnesium, calcium, and trace elements. Paddle wheels gently agitate the ponds to expose the microalgae to maximum Hawaiian sunlight, while the nutrient boost from deep seawater accelerates growth. Spirulina thrives in this alkaline, mineral-rich medium, doubling biomass every few days in a continuous 5 to 7 day harvest cycle. The cold deep seawater also cools the ponds, preventing overheating, and powers their patented ocean chill drying process, which uses chilled air to preserve nutrients without oxidation. The result? Hawaiian Spirulina pacifica and Bioastin astaxanthin, packed with protein, 60 to 70%, antioxidants, and over 100 nutrients. Produced year-round at scales that make Cyanotech one of NELHA's biggest success stories. In short, the mechanism is elegantly straightforward. Pump, flow, renew. The deep seawater provides temperature control, sterility, oxygenation, and a natural nutrient cocktail that lets cold water species grow faster, healthier, and cleaner than anywhere else. It's not magic. It's ocean science engineered to perfection. So, you're probably asking the questions everyone wants answered. How much do they actually produce? How much money does this make? And who on earth is buying all this stuff grown on a lava field in Hawaii? The answers are bigger and more impressive than you might expect. Across NELHA's host park, the combined annual production from its key tenants reaches tens of thousands of tons of premium aquaculture and superfood products. This includes millions of pounds of high-quality spirulina and astaxanthin microalgae, several million individual abalone reaching prime market size, and thousands of pounds of healthy, live Maine lobsters, plus ongoing holding and revival operations for premium shipments. These aren't small backyard yields. They represent some of the most valuable per-pound seafood and health supplements on the planet. Where does it all go? The abalone, prized for its tender, buttery meat and striking red shells, heads mostly to Japan and China, where it fetches top dollar in high-end restaurants and luxury markets. Maine lobsters, kept alive and vibrant in the cold deep seawater, are flown fresh or live to seafood distributors across the United States, Canada, Asia, and Europe, landing on tables in Michelin-starred kitchens and upscale supermarkets. Spirulina and astaxanthin from Cyanotech Corporation go global. You'll find Hawaiian Spirulina pacifica and Bioastin in health food stores, pharmacies, and online across the US, Europe, Japan, Australia, and emerging markets in Southeast Asia, sold as premium supplements for immunity, antioxidants, eye health, and skincare. And the money? The serious business. Cyanotech alone has reported annual revenues consistently in the $30 to $50 million range in recent years, driven by the high demand for its nutrient-dense, ocean-chilled products. Big Island Abalone exports millions of abalone annually, generating multi-million-dollar returns from premium pricing, $50 100 plus per kilogram. When you add up all the tenants, plus jobs, tourism, and research spin-offs, NELHA contributes roughly $150 million to Hawaii's economy each year, per the latest University of Hawaii Economic Research Organization estimates. That's not pocket change for a facility built on what was once considered worthless lava rock. The real payoff, though, goes far beyond dollars. By tapping deep seawater, these farms use up to 95% less water than conventional systems. No freshwater diverted, no massive ponds evaporating in the sun. Disease is almost non-existent thanks to the ultra-clean source, meaning zero antibiotics and zero chemical treatments, delivering cleaner, safer food. Growth is faster, 20 to 50% quicker cycles. Yields are higher per square foot, and the environmental footprint is tiny. Returned water is only slightly warmer and naturally nutrient depleted, with no runoff pollution. Every groundbreaking project has its shadows, and NELHA is no exception. The system is remarkably robust, but it isn't invincible. One of the biggest challenges is water quality variability. In recent years, notably 2021 to 2024, subtle shifts in deep ocean currents and nutrient levels caused occasional spikes in bacteria or changes in plankton composition, which reduced survival rates for delicate abalone larvae and lobster juveniles by 20 to 30% in affected batches. NELHA responded quickly with enhanced filtration, real-time monitoring, and backup blending systems. But these incidents highlight how dependent the entire operation is on the natural chemistry of the deep sea. Infrastructure risks are another concern. The massive pipelines endure extreme pressure, saltwater corrosion, and occasional seismic tremors from Hawaii's active volcanoes. Maintenance costs run into millions of dollars annually, and any major repair or downtime could halt production for weeks. Hurricanes, rare but powerful in the Pacific, pose a threat to surface facilities, while energy costs for pumping hundreds of thousands of gallons per minute remain significant, even with efficient modern pumps. Despite these hurdles, the NELHA model has inspired replication around the world. Japan operates similar deep-sea water systems on Okinawa and Kumijima, using cold upwelled water for aquaculture and air conditioning. South Korea's Jeju Island has built comparable facilities for abalone and seaweed farming. Experimental projects in California, Norway, and the Canary Islands are testing deep ocean water for cooling and food production. In arid regions like the Middle East, countries such as the UAE and Saudi Arabia are exploring adaptations of the technology to grow high-value crops in desert environments. The core idea, harnessing cold, nutrient-rich deep water, has proven adaptable far beyond Hawaii's volcanic shores. What lessons can the rest of the world take away? First, bold investment in long-term infrastructure pays off. NELHA took decades and hundreds of millions of dollars, but today it generates sustainable economic returns and jobs while reducing resource strain. Second, nature often holds the answers. Deep seawater is a free, renewable resource that outperforms artificial cooling and fertilization in many ways. Third, continuous monitoring and adaptability are essential. The ocean is dynamic and success requires science, not just engineering. In the end, NELHA stands as a testament to human ingenuity, a place where the deepest, coldest waters of the Pacific meet the hottest lava fields on land, and together they create abundance where none should exist. It's not a perfect system, but it's a powerful proof of concept, one that may help shape how we feed and sustain ourselves in a changing world. Don't forget to hit that like button, subscribe to the channel, and turn on the notification bell so you never miss an upload. Thank you so much for watching all the way through. See you in the next one.